Hello, George Romanic here. In today's video we are going to talk about total differentiation of a vector in a rotating frame of reference. As Professor Arthur Matok from MIT said, this is what separates boys from men and girls from women. You can go and carry out total differentiation of a vector in an inertial frame of reference, and that's something that you do daily in physics and mathematics problems. When you switch from inertial to non-inertial frame of reference, and in today's video we are dealing with a rotating frame of reference as a special case of a non-inertial frame of reference, things get more complicated. You have to take into consideration that rotation. And that's what we will do today. So we will extend total differentiation operator to account for non-inertial frame of reference and the special case of a rotating non-inertial frame of reference. Okay, what is inertial, what is non-inertial reference frame? I talked about that before, you can also Google it and so on. Inertial frame of reference is the one that is static or moving at uniform velocity in a straight line, because Albert Einstein taught us there is no difference between moving at uniform velocity and standing still. Then, on the other hand, a non-inertial reference frame is the one that doesn't obey these rules, namely, frame of reference that is accelerating. Now, acceleration can be along straight line, which is actually more often more complicated than the case of rotation. If you are rotating, you have to accelerate to get some centripetal acceleration to stay in orbit, to so to speak, in rotation. And therefore you are a non-inertial frame of reference. Why do we care? You might say, well, this is atmospheric science and oceanography and wind energy channel, and all these things, wind, for example, is a vector, wind speed is a vector, wind velocity is a vector, and it is we measure it relative to Earth. But Earth is rotating, so you see Earth is non-inertial frame of reference. If you take sun, center of the sun, as the ultimate truth, then you can say, okay, that is my inertial frame of reference. Of course, somebody sitting in the middle of Andromeda galaxy could say, well, not really, because sun is moving around the galaxy. You say, okay, I'll take center of the Milky Way to be inertial frame of reference, but somebody from the Great Attractor or Andromeda galaxy could say, but wait a minute, you are also moving, accelerating, and it goes forever. So in that case, you have to take something to be absolute truth. In this case, we are saying, for example, sun is inertial frame of reference, and when you look at you and me from the sun, you see that we are rotating around the axis of the Earth, because Earth is rotating counterclockwise. How to take that into consideration? Because, as we will see today, total differentiation of a vector is not the same in inertial and non-inertial frame of reference. That's something that we will derive today. In our derivation, I will use this little friend a lot, globe, to demonstrate the orientation and direction of unit vectors in a quasi-Cartesian coordinate system. I say quasi because it will rotate with the Earth, which means it's not purely Cartesian coordinate system. If this is not clear what I said now, I understand it will become much clearer when I start deriving these concepts. So let's start. Here is the setup of our problem. I have generic vector A and two coordinate systems. One is inertial, and I will use prime variables to indicate inertial reference frame, and I have non-inertial, that is rotating in this particular case, coordinate system. And I will use variables without primes to indicate this coordinate system. Each coordinate system has unit vectors I prime, j prime, k prime, and this one has I, j, k, and I use these red arrows to indicate these unit vectors. In this inertial frame of reference, vector A can be expressed as I prime AX prime plus J prime AY prime and plus K prime AK prime, where AX prime, AY prime and AK prime are components of this vector along X prime, Y prime and Z prime respectively. Simple business. Now vector A, same vector A, in this rotating coordinate system is clearly IAX plus JAY plus KAZ. Now let's find total derivative of A in this inertial reference frame. That would be d in inertial, I will use this for inertial, of A dt is equal I prime d AX prime dt plus J prime d AY prime dt and plus K prime dAz, here should be z, it's okay, dt. A is also expressed in rotating coordinate system. So the question that we ask ourselves is, what would be total differentiation of A in inertial reference frame if A is expressed in rotating reference frame? That would be d in inertial of A dt is equal, well, I make differentiation of these components AX, AY, AZ, so that would be I dAX dt plus J dAY dt and plus K dAz dt. But from the point of view of inertial reference frame, these unit vectors are also changing because this is rotating frame of reference. Namely, if this is this rotating frame in point of time t, then in the next point, perhaps, this will be y-axis, this will be z-axis, and this will be x-axis, which means that these unit vectors will accordingly rotate. So we have to take that into account and we get total differentiation in inertial frame of reference of vector I times the component AX plus di of j dt times AY and plus d in inertial frame of reference of unit vector k dt and times AZ. Now kindly notice that this over here is simply differentiation of vector A in rotating coordinate system. So we can say that di of A dt is equal dr of A dt. So this is differentiation of vector A in rotating coordinate system in this one, and plus these three terms. So we reduced a little bit complexity of this expression to this form, and this is now where we need to be careful, because the derivatives of these unit vectors can be very nasty depending on the behavior of this coordinate system. You see, let's assume that instead of this simple rotation, this coordinate system exhibits this motion in time. Then good luck finding some nice expression for the derivatives of these unit vectors in time. Fortunately, we are applying this analysis for our beautiful planet Earth, and it is just rotating. And in the case of simple rotation, we can find relatively nice expressions for time derivatives of these unit vectors. And that's exactly what we will do now. Now let's establish some definitions that are applicable to our spherical Earth. We will say that I is positive eastward, J is positive northward, and K is positive upward. Very well. Now, we have to investigate term by term these time derivatives of unit vectors. Let's first look into di dt. So I is unit vector positive eastward, which means if this is our planet, this is the I vector, positive eastward. And Earth is rotating in counterclockwise direction. So you can see as Earth is rotating, I vector is rotating together with the Earth. And very important to notice that there is no change of I vector along the latitude or along the height. The only change is with the rotation of the Earth that is counterclockwise. Which means, while in principle I could say that change in I can be delta I over delta lambda, where lambda is longitude, times the change of longitude, delta lambda, plus delta I over delta phi, where phi is latitude, times the change of latitude, and plus delta I over delta z times change delta z, where z is height. I just showed you these terms do not exist in our case because our planet is rotating in counterclockwise like this. If our planet was rotating like that and at the same time maybe did this wobbling, then these terms would exist. But because rotation is purely like that, there is only this term when it comes to change of delta I. Now what I will do here, I will divide this by delta t, which is time, and let delta t go to 0. That will give me the derivative d in inertial frame of reference, di dt equals, well, delta I, delta lambda times d lambda, this over dt. Okay, but what is d lambda dt? That is simply angular velocity of Earth. D lambda dt is omega, angular velocity of Earth. Again, if we take our globe, unit vector I was here, and then after some time dt, it moved here. Well, it moved here thanks to rotation of the Earth, and how fast it moved there is dictated by the angular velocity of the Earth. In other words, d lambda dt is omega, which means that di of I dt is equal omega delta I delta lambda. Now we need to find this delta I delta lambda. And to do that, I'll use another page and I will use again model of my Earth. Let's say we are here somewhere in Canada, let's say in Montreal at this latitude, and this is how I changes as Earth rotates. So if we are looking at the situation that I just showed you from the North Pole, so to speak, from the top, then the picture that depicts this is the following. Here I have a part of the circumference of the Earth. Here is the center of rotation, so this is top view. Here is my vector I. It is tangent to the curvature. And here is my vector I plus delta I. So this over here is I plus delta I as Earth rotated like this in counterclockwise direction. This is the angle for which Earth rotated, so this is delta lambda, change of longitude, and this over here is r cosine phi, where r is radius of Earth. Now you might say, wait, how did you come up with the fact that this is r cosine phi? Don't panic, I'll show you now. If we look at the side view, so this was top view, let's look 1/4, so to speak, of the Earth. Earth rotates like this with the angular velocity omega, and I'm sitting here in Montreal. This is my latitude, phi, and I am rotating into the page, so to speak, as I just demonstrated. This is radius of the Earth r. So if I look at this from the top, okay, top view, I will see that this is the distance from the axis of rotation. And I hope that you can see that this distance is r cosine phi. And that's how we get that this is r cosine phi and not r. Okay, now what we go back to this top view picture. What we want to find is this delta I. Well, that's simple, because I know this was my I at the time t, so I just translate that I over here. So I translate this vector over here, and look, my delta I is this vector over here. I messed up, so this is this vector over here is I plus delta I, and this vector over here is delta I. Now notice that this vector delta I is pointing towards the axis of rotation, not away, which means on this, well, this is side view, let's write it down, this is side view. So on this side view picture, this would be that vector delta I, this vector. And now finally I can decompose this vector delta I into k direction, because this is my unit vector k. Remember here I told you that k is positive upward and j is positive northward. So j will be like this, which means this is projection of vector delta I along the k direction, and this is projection along the j direction. I hope you can see these things. So from figure I can conclude that this delta I over delta lambda is equal, well, this projection of vector delta I, let me use different color perhaps, this, and that is clearly negative k cosine phi. Why negative k? Because it's the opposite direction of positive k, and if this is angle phi, then this is also angle phi over here. And here we have another component of this vector delta I, so this is vector delta I, as I said many times, and this component is j sine phi. That's simple. Why positive? Well, it's in the positive direction of j. So this is equal j sine phi minus k cosine phi. Now we can combine this result with our previous page, namely this, to write acceleration of unit vector I in inertial frame of reference is equal omega, that comes from the previous page, j sine phi minus k cosine phi. Very nice result. But you can also express this in a more compact form in terms of cross product, and it's always nice to write equations in vector form because then you can print them out on your t-shirt and go to disco club to show off that you know vector calculus. What I mean by that is the following. If I replicate this figure one more time here, then this is quarter of the Earth that I showed. I'm sitting over here in Montreal and I have angular velocity omega just like everybody else on this planet Earth. So Earth is rotating in counterclockwise direction. Now remember, unit vector k, I'm making it large so you can see it nicely. This is unit vector k. This is unit vector j. This is latitude phi. This is radius of the Earth r. Well, I can find components of this omega along the j direction and along k direction. If this is angle phi, then this is also angle phi over here. So from figure, we see that omega as a vector now, not scalar, as a vector, has components. Well, it has 0 in the I direction, because that's the direction in which the Earth rotates. Now, in the j direction, it has this component over here, and I hope you can see that is omega cosine phi. And in the k direction has this component over here, and I hope you can see that is omega sine phi. And I already explained this several times in my videos, so centrifugal force, Coriolis force, Rossby number, and so on. So combining this with this over here, we can write that di of my unit vector I dt is equal omega cross I. And this is very important result because after all this talking, we finally found acceleration of vector I in inertial frame of reference. It's omega cross I. Now, some of you might say, wait a minute. How did you conclude that this is vector product if two vectors have these components? Now, I could be one of these YouTubers that says, I leave that to you to demonstrate, but I'm not going to do that. I will demonstrate that for you. What is omega cross I? Well, that is, we can use determinants. First row will be unit vectors, I, j, k. You know the drill. Second row will be components of omega, and that is 0, omega cosine phi, omega sine phi. And the third row is component of vector I, that's unit vector. It only has component in its own direction, 0, 0. And now I solve this determinant. In the I direction, I have 0 minus 0. Minus, in the j direction, I have 0 minus this times this is omega sine phi. Plus, in the k direction, I cross this column and this row, I have 0 minus omega cosine phi. So you see there is nothing in the I direction. In the j direction, minus and minus will give me omega sine phi. Well, that's good. That's what I have here. And in the k direction, I should have negative omega cosine phi k, and that's exactly what I have here. So you see, I convinced you that this cross product is equal this. Now, without convincing you any further, I can tell you that you can use exactly same reasoning to show that derivative in inertial frame of reference of j is omega cross j, and derivative in inertial frame of reference of k is omega cross k. But I will not spend time now demonstrating this because it's absolutely the same reasoning that I used to demonstrate this guy over here. Now our work is almost done. What we need to do is go back to this page and remember that this is our equation from which we started explaining all these things. So instead of this, I use di dt that I derived here. Instead of this term, I use dj dt that is here. And instead of this term, I use this expression over here. And I can write final result over here. That should be right here next to subscribe button, I believe, if you want to click on that. It will tell you that di of vector I in inertial frame of reference is equal derivative of vector A in the rotating frame of reference plus omega cross A. And look at this beautiful expression. Of course, I hope you, let me clarify this too. I hope you see how I got A over here, because I have I, J, K over here. And when I combine them with this AX, AY, AZ, you will see that will give me vector A. We can also go one step further and put this in the form of an operator that will give us that differentiation in inertial reference frame is differentiation in rotating reference frame plus omega cross whatever you are operating on. Now, one simple question. How do we know that this operator only operates on vectors? Answer: because cross product can only operate on vectors. If you put here temperature, then you should immediately fail your exam, because you are saying that vector can have cross product with scalar, and that's a no-no. Another very important result. Very important result. If we have inertial and rotating reference frames, looking at a scalar, not vector, looking at a scalar, let's say there is temperature over here. It doesn't matter if I look at temperature from inertial, rotating, or some completely crazy coordinate system. Temperature is temperature. If you are looking at a vector, then it matters so much if you are looking from inertial, rotating, or some crazy coordinate system. And you can clearly see that from here. If I don't have vector, if I have scalar, then this term disappears. And look, derivative of a scalar, imagine this is scalar, derivative of a scalar in inertial and rotating reference frames, it's the same. But when I have vector, I get this term here that makes everything nasty. This is relatively nasty because we only have rotation. If we have something more than rotation, some crazy accelerations, then you cannot find closed form expression for these derivatives that I talked about before. The video is not the easiest one that you will find on this channel, but that's just how the nature is. Some of the videos and subjects are more complicated than the others. We adapt and we try to learn. Until next video, goodbye.